My name is Anna Martin, and I will be talking about uniform circular motion and do a few examples dealing with the principles with uniform circular motion. So basically, any object moving in a circle at a constant speed is experiencing uniform circular motion. Okay, so I'm just going to start out with a circle here. Okay, here's the center of my circle. Here's the radius of r. And I have an object on my circle. And now this object is moving around my circle. So the velocity of this object, I'm going to go ahead and draw this, the velocity vector v. This v is its tangential velocity, which is basically just the speed the block is moving at. But to stay in this circular pattern, the velocity has to be constantly kind of changing and curving to stay on this circle. So the change in direction of the velocity means that it's accelerating. Well, the direction of the acceleration is pointed directly at the center of the circle. And this acceleration is called centripetal acceleration. Okay, so we know force, the equation for force is equal to mass times acceleration, correct? Okay, well, since the acceleration is pointing towards the center of the circle, that means that the net force on an object in uniform circular motion is directed towards the center of the circle. So the force acting on any object in uniform circular motion, its net force is always going to be pointing towards the center of the circle. And this force is also called centripetal force. Well, then you might be asking, well, then why do I feel like I'm flung away from the circle, or let's say flung to the outside if you're, let's say, in a car making a U-turn? This is actually a fake force called a centrifugal force. It's not actually real. So basically why this is happening is you have this tangential velocity, right? But you have a car around you, and this car is moving in a circle. So you want to keep going straight, but the car that's moving in a circle is kind of pulling you in, just kind of like the acceleration is just pulling you in that circular motion. In addition, we are going to go over some of the formulas associated with uniform circular motion. So let me kind of erase some of this stuff here. Erase the title. Okay. So the acceleration towards the center of the circle is called centripetal acceleration. Okay, and the formula for centripetal acceleration is acceleration is equal to the tangential velocity squared over the radius. Okay, and so your equation for your tangential velocity is going to be velocity is equal to your circumference, 2 pi radius over time. Okay, and so I talked about centripetal force. So you know that your force is equal to mass times acceleration we talked about earlier. Well, you know what your acceleration is, so I'm just going to plug that in. So that's centripetal force is equal to mass times your tangential velocity squared over your radius. And that is your equation for centripetal force. Okay, and now we're going to do a few quick examples. Okay, A racing car is moving around a circular track of a radius of 300 meters. At the instant when the car's velocity is directed due east, its acceleration is directed due south and has a magnitude of 3 meters per second squared. Is the car moving counterclockwise or clockwise, and at what speed is it moving in this direction? Okay, so to start off, I'm just gonna draw our circle. Here's the center, and it said it had a radius of 300 meters. Okay, so at the instant we're talking about, the car's velocity is directed due east. Okay, so we know due east is this way, right? Okay, and it also says its acceleration is due south. We know south is down. Okay, so we also know that the acceleration of an object in uniform circular motion is always pointed towards the center of the circle. And since our acceleration is south, which is straight down, that means it has to be directly on top of the center, so that way the acceleration is pointed directly at the center. Okay, so our acceleration is here at 3 meters per second squared. And now we need to know what direction, or which way around the circle that the object is moving. Let me draw my object here. Okay, so it's going east, and we know east is to the right. So this part is pretty simple in that we know that our object is just going to be moving this way. Okay, so it's asking us at what speed is the object moving. So when it says speed, it's just talking about your tangential velocity. Okay, so we know acceleration. Acceleration is equal to 3 meters per second squared. But we also know that the equation for centripetal acceleration is tangential velocity squared over radius. Well, that's perfect because we are looking for this tangential velocity right here. Okay, so we know acceleration and we know radius, so we just have to solve for this tangential velocity right here. So I'm going to multiply r onto the other side. So acceleration times radius is equal to velocity squared. And then we have the square root of acceleration times radius is equal to the tangential velocity. So I'm just going to plug in my numbers here. So the square root of, our acceleration is 3, and then our radius is 300 meters, and all my units are already correct. So 3 times 300 is equal to our velocity. And I can simplify that in my head, and I know that the square root of that is 30, and then our units are meters per second. Okay, so this 30 meters per second is our tangential velocity of our car on this track. And we know that it is moving clockwise because it is traveling due east, and this way is clockwise. Okay, time for our next example. Okay, so a ball attached to a string is whirled around in a horizontal circle with a radius r. If the radius is changed to 4r and the same centripetal force is applied by the string, what is the new speed of the ball? Okay, so first I'm going to draw the path of the ball. Here's our ball right here, center of the circle, and here's the string that the ball is on with a radius of r. Okay, so what we know is that the radius is being changed to 4r. So I'm just going to write that up here. But the same force is being applied. So the force initial is equal to the force final. Okay, so we know that the force initial is just mass times acceleration. So, and we know that our initial acceleration is just going to be your initial tangential velocity over r. And I'm going to say that this is your initial velocity. Okay, so on the other side of the equation, I'm going to have mass times my final velocity squared over 4r. So I'm going to multiply 4 onto the other side. So I'm going to have 4, and the r's are going to cancel out when I multiply it over here. So I'm going to have 4 mass times initial velocity squared is equal to the mass times the final velocity squared. Okay, so I know that these masses are going to cancel out right here, so I'm going to be left with 4 initial tangential velocity squared is equal to the final tangential velocity squared. Okay, so then I'm just going to take the square root of each side. And I know that my final velocity is going to be twice the original velocity. So there we have it. Your final is going to be twice your initial when we change the radius from just r to 4r. Okay, and one final example here. Okay. A child whirls around a toy at the end of a string of length r in a horizontal circular path at a constant speed. The toy completes each revolution at a time period t. What is the magnitude of the acceleration of the toy in terms of r and t? Okay, so this one is just a fairly simple problem, no actual numbers to work with. Okay, so center of our path, we have a string and it tells us that our length is r. I'm going to say our object is right here. And, okay, so the time it takes for an object to get all the way around the circle is just t. So we're given t and r, and we're trying to find the acceleration. Okay, so we know acceleration, centripetal acceleration, is the same or is equal to your tangential velocity squared over your radius. Okay, well, we can't have velocity in our answer. We need to find velocity in terms of t. So we know that your tangential velocity is equal to your circumference over your time. Well, that's good because we have r and t right here. Oh, let me make this capital. Okay, so now our velocity is in terms of r and t, so all we have to do is plug it back in, and then we'll have our answer. So our acceleration is equal to velocity squared, so that's 2 pi radius over time squared times 1 over our radius. So our acceleration is going to be 4 pi squared times r radius squared over time squared times 1 over our radius. So our acceleration is going to be equal to, I can cross out one of these r's. So we're going to have 4 pi squared r over our time squared. And that is going to be the acceleration of the toy when it's being flung around the circle. And you can actually use this as another formula for any other problems. Okay, thank you. I hope that helped with understanding circular motion.